everyone, welcome to this presentation. Today we're going to see how to solve steady-state heat flow problems using FEMM. This is the outline of this presentation. We will see first, as usual, an introduction, then the analysis example, and finally the results. These are two relevant videos related to this topic. One is FEMM1, air core inductor. In this video you can see how to do the drawings and how to use the basic resources of the program. And physics number 6, Maxwell's equations in matter, that we saw the other day. So this is also relevant to understand the analysis that we are going to do today. In this video, physics number 6, we saw the Maxwell's equations in matter, and we saw that for the case of electrostatics, we have the derivatives of the fields with respect to time equal to 0. So we have this equation is the divergence of Ke is equal to the charge density of free charges divided by epsilon sub 0. We have that the curl of E is equal to 0, and because of this equation we can say that E can be obtained as the gradient of a potential V. If we substitute this in this other equation, then we get the final equation that we have to solve for electrostatics, which is that the divergence of K times the gradient of V is equal to minus rho sub F divided by epsilon sub 0, where K, as we know, is the dielectric constant. And now, in the case of heat transfer, we have an equivalent problem as the electrostatics problem. Instead of having the electric field E, we have J, which is the heat flow or heat flux density, and is measured in watts per square meter. And instead of a distribution of charge, we have Q sub V, which is the heat produced by the source per unit volume and per second, which is measured in watts per cubic meter. So we can say that the divergence of J is equal to Q sub V. So it's like this. We have Q sub V, which is the source of heat, and then we have the field J. So if we apply here the Gauss theorem, we can say that the total flux of J out of a closed surface S is equal to the total heat produced by the source, which is measured here in watts. And the curl of J is equal to 0 also, so we can say that J can be obtained from a gradient, which is the gradient of the temperature, and K here is the thermal conductivity of the material. So if we take this again into this equation, we get this other equation, which is that the divergence of K times the gradient of T is equal to minus Q sub V. This is the equation that we have to solve in this kind of problems in order to get the value of the scalar field, which is the temperature. K is the thermal conductivity and is measured in watts per meter and per Kelvin. So we can see that both problems are equivalent. The electrostatics problem has this equation and the heat transfer has this equivalent equation. So this is the reason why any program of finite element analysis can be used to solve both electrostatics problems and heat transfer problems. In heat transfer problems, we have to study not only the heat transfer between solids, but also the flow of heat due to the movement of a fluid. So we have a fluid here surrounding a solid, and then we are going to have a transfer of heat between them. So in this case, the flow of heat can be expressed as a coefficient H times the difference in temperature. This coefficient H is the heat transfer coefficient and is measured in watts times square meter per Kelvin. And because we know that the heat flow density is equal to minus K times the gradient of T, we can substitute this here, and then we get this equation, which is the equation that the program has to solve in order to calculate the temperature T. And this heat transfer process is also analyzed by FEMM. We can see in this window here, boundary property, we have this part corresponding to convection. This is the equation, which is the same as this one here. And here we have to include the parameters of H, the coefficient, and the temperature of the fluid. And FEMM can also consider the radiative heat transfer. So if we have here a material at a temperature T and another material here at a temperature T sub 0, the heat flow density is beta, the radiation view factor, times the Stefan-Boltzmann constant, and times the difference between T raised to 4 minus T sub 0 raised to 4. This is when we are considering black body radiation. So then again, because J is equal to minus K, the gradient of T, we have this equation, and in this window of the program corresponding to boundary property, we have here radiation. This is the equation, and we have two parameters. One is beta, and the other one is T sub 0. So let's see now an example of analysis with FEMM. We are going to analyze the behavior of a heatsink. Here we have the drawing of the heatsink with the dimensions, and we are going to analyze what happens when we place here an element that is generating heat into the heatsink. From the manufacturer's data sheet, we can obtain this characteristic of the thermal resistance of the heatsink as a function of the length. We are going to consider that the length is 100 millimeter, so the expected value of the thermal resistance will be 6 Kelvin per watt. And to do our analysis, we are going to consider that we have a source of heat of 10 watts, and we are applying this heat into the heatsink, and the ambient temperature is 25 degrees. So this is the equivalent circuit that we have to analyze this type of problem manually. So from this circuit, we can calculate the heatsink temperature as shown here, and substituting the different values, we get that the heatsink temperature will be 85 degrees. Now we are going to analyze the problem using FEMM and see if we can obtain the heatsink temperature, and from it we can calculate the thermal resistance of the heatsink. And here we have the problem of the heatsink. We can see the drawing. Actually, we could have only drawn the half of the heatsink because we have symmetry, but I preferred to draw everything, and then we can see the complete behavior of the heatsink, because at the end it's a simple problem and we can do the complete drawing very easily. So the drawing is very easy to be done. There is information about how to do this in the first program of this series. So if you don't know how to do it, please take a look at this video, FEMM number 1. So this is the drawing, and what we have done is to draw here this separate line, which is the line corresponding to the object that is emitting the heat into the heatsink. So for example, we are going to place here a transistor or a diode that is going to be emitting the heat into the heatsink. So now we can see, for example, the definition of the problem. So we have defined it as a planar problem, dimensions in millimeters, the depth is the length of the heatsink, 100 millimeters, and we can leave these other things by default. So say OK. Now we have to add the materials that we have in our problem. In this case, we have the heatsink, so this is going to be made of aluminum. So we go to Properties, Materials Library, and we select metallic, then aluminum, pure aluminum. We drag this and say OK. And now, using this button here, we place a point inside the heatsink. Right click to select, spacebar, and we add here aluminum. We are going to select here at this first try the default mesh size. So we say OK here. And now we have to define the boundaries that we have in our problem. We have two boundaries here. One is the boundary between the air surrounding the heatsink, and the other boundary is this one here, which is the one which is emitting the heat into the heatsink. For the boundaries, we have to do some calculations first. In the case of the device which is here emitting the heat, we are considering that it has a width of 4 millimeters. So it's something like this. We have 4 millimeters wide. The length is 100 millimeters. So the area that we have here emitting the heat is 400 millimeters squared. The power is 10 watts. So the heat flow density is 25 times 10 to 3 watts per square meter. So we can go to the program now and put this value in our boundary. So now we go back to the program, select properties, boundary, and we are going to create a new boundary. So add property. The boundary, for example, we can call this boundary heat flux. The type of boundary is heat flux, and here we have to put the value of the heat flux, but I have found that we have to put here a negative value, otherwise it's not going to work well. I don't know exactly why. I didn't find any information about this, but we need to introduce here minus 25 E3 and say OK and OK again. Now we select the line tool here. We select this area, right click on it, and then press spacebar, and then we assign this heat flux to it and say OK. For the other boundary between the air and the heatsink, we have the convection process. So we need the heat transfer coefficient H. This coefficient is more difficult to calculate with accuracy. It depends on many things: the type of fluid, the flow regime, the thermohydraulic conditions, and so on. So it's related to the process of exchanging heat between the solid and a fluid surrounding this solid. And this process occurs in the boundary layer between them. So at this point we have the solid temperature, and then the temperature is decreasing inside the layer until reaching the ambient temperature, the fluid temperature. Here we have some values of H in different conditions in air when we are forcing the air along the plate, along the solid, and in the case of water. So we have these ranges, and we can find more information in the literature about this kind of heat transfer process. But fortunately, in the internet we have calculators to get the value of H in different conditions. I have selected this calculator from QuickField. This is the link to this calculator. And here we can introduce the type of heat transfer process that we have. In this case, it's a vertical plane, the length, the temperature of the surface. Here we have selected 80 degrees approximately. This is the temperature of the air, the surrounding fluid, the type of fluid, in this case air. So we press here, calculate, and then we get the value of H. And if we want, we can get the different intermediate results, the film temperature, different parameters, different numbers that are used for these calculations: the Planck number, the Grashof number, the Rayleigh number, the Nusselt number, so quite complex calculations and also based on experimental verification. So we get this value here, 10.5. Let's try, for example, 10 for our analysis. So now we go to the program, go to Properties, again, Boundary, and we are going to add a new boundary. We are going to call this, for example, air boundary. Now we go to the type of boundary, convection, and the value of H, and the temperature is 25 degrees, which is 298 Kelvin. We say OK here, OK again, and now we select all the boundaries that are going to be in contact with the air. So we go to this button, we select here line, and then we select all the lines, press Ctrl to do a multiple selection. We select all of them. Now we press spacebar and we select air boundary and say OK. And now we are ready to run the analysis. So we go to this button here, click on it to create the mesh. So here we have the mesh with the default values. And now we go here, click on this button to do the analysis. So the analysis has already been done, and we can press this other button here to see the results. So we click on it, and here we have the results. So we can see in different colors the temperature of the heatsink. Here we have the different values. There is not much different from the maximum value and the minimum value, so it's something like 356 Kelvin. So it's very similar to the value that we are expecting. We can go and show, for example, here we can do a contour plot showing the equipotential lines. Say OK, so we can see the lines of constant temperature. We can click on any point and see the different values, the coordinates, the temperature, the heat flux with its components, the temperature gradient with its components, and then the value of the conductivity in both directions. We can do other things. For example, we can obtain the average temperature in the heatsink. For this, we can select here this button, then select the heatsink. We go to integral, and then we can calculate several things. For example, the average temperature over volume, or other things like the volume, and so on. So let's calculate, for example, the average temperature. So the average temperature is 356 Kelvin. The value that we calculated with the model, with the equivalent electrical model, was 358. So it's quite similar. We can do other things. For example, we select the line tool, and then we select a line starting from this point to this point, and then we can calculate several things. For example, here we can calculate the temperature difference, but we can calculate also the heat flux. So we select, for example, this one and say OK. So the heat flux that we are having through this surface is 8.6 watt, but actually we designed it to have a heat flux of 10 watts, so there is some difference. I have investigated this, and this difference is related to the size of the mesh that we are generating. So if we go back and then select here the material tool, select the aluminum, spacebar, and then we can do here, we can instruct the program to do a mesh size smaller. For example, select 0.1 millimeter. We say OK. We generate the MEX again. So we can see that we have many more nodes. Say OK here. So we run the analysis again. It's going to take more time, of course. Go back to the results. And then we can try again to calculate the heat flux in this area. Go to integral, select the heat flux, say OK, and now we have a more accurate value, 9.3 watts. But at the end, the difference in the temperature is not so high, so we have almost the same value of 356 Kelvin. Let's see now another way to do the definition of the problem. Now, instead of considering that we have a surface here emitting the heat, we are going to consider that we have a volumetric device here, which is like this. We have 4 millimeters width, 1 millimeter height, and then 100 millimeters depth. So the volume is 400 cubic millimeters. So the volumetric heat density can be calculated as shown here, which is 25 times 10 to 6 watts per cubic meter. And here we have the problem defined in this way. So we have added here this chip. We have selected copper material in this case here. So what we have done is to go to properties. In materials library, we have added here copper material. Okay. And then if we go to properties, materials, we select copper and we select here modify property. So what we have done is to add here the volume heat generation corresponding to this chip of copper, which is then, as we have seen, 25E6. So we say OK here, OK, and now we can generate the mesh, say OK, and then run the analysis and go to the results again, and here we can see the results, so they are very similar. We can select the volume corresponding to the heatsink, go to integral, select average temperature over volume, and then we can see that the result is very similar, 353.9 Kelvin. Okay, we can calculate the heat flux going into the heatsink. So for this, we can select the line tool, select this line from this point to this point, go to integral, heat flux, OK, and we can see that the heat flux is 8.6 watts, similar to the value that we have obtained before with this mesh. Here we can see a comparison of both results using the heat flow density through this surface and using the heat volume density of a chip here placed on the heatsink. So we can see that the results are very, very similar. Finally, the objective of this type of analysis is to get the thermal resistance that we are going to have for our heatsink. So for this, as we have seen, we can select the volume tool here, then we select integral, we choose average temperature over volume, we obtain the average temperature of the heatsink, and then in our model we can calculate the value of the thermal resistance of our heatsink, which is 5.8 Kelvin per watt. So it's very similar to the value that we found in the manufacturer's data sheet. Well, this concludes this presentation today. All the files are going to be available on my GitHub website. The link will be on the comments section of this video. Please let me know if you have any comment or question. I hope that this information is useful for you. Thanks for watching, and I hope to see you in the next video. Goodbye now.